So now that we're comfortable with exponential and logarithmic functions, we want to be able to use properties about them to actually solve equations. So there's going to be some kind of set ways we can work with each, but a lot of it is going to be a trial and error. What tools can I use for this specific type of equation? And the one thing you have to be careful about, especially with logarithms, is you might get extraneous solutions, because logarithms aren't defined at 0 or for negative values. So you need to make sure you're checking your solution when it's possible. So let's start with some exponential equations. Let's solve each of these equations exactly. So we're going to start with 169 to the x power equaling 13. Now the best thing you can do, if possible, is see if you can write them with the same base. And in this case, 169 is 13 squared. So both sides of the equation can be written to the same basis. 169 is 13 squared, so that's 13 squared to the x power equals 13. And when you take an exponent to an exponent, you just multiply the two together. And 13 is the same thing as 13 to the first power. So the only way these two sides will be equal is if those exponents are equal to each other. So because they're the same bases, we can equate the exponents. So really the solution to this will be 2x equals 1, or dividing by 2 gives us x equals 1/2. So you don't need to go through and check this answer. You can if you have time, but this isn't going to give us anything extraneous. So let's go ahead and try this next one. We've got 3 times 3 to the 4x equals 27. So good thing on that right-hand side, I can write that in base 3. And over here, because I have 3 times 3 to the 4x, this is just like 3 to the first power. When you take a base and multiply it by something that has the same base, you add those exponents. So that's 3 to the 4x plus 1, and then 27 can be written as 3 cubed. So same thing, I've got the same base on both sides. That means those exponents must be equal. So solving this leads to solving 4x plus 1 equals 3, or 4x equals 2, or just x equals 2 over 4, or 1/2. So 1/2 will be the value that solves this original equation, okay? Now in this next example, we run into a bit of an issue because I've got base e on one side and I've got 17 on the other. So there's going to be no way I can write them with exactly the same base. So instead what we're going to do is we're going to take logarithms, and that's going to allow us to get an exact answer and also a decimal approximation if you plug it into your calculator. But our directions told us to solve each equation exactly, so I don't want to plug into a calculator. Instead, what we're going to do is we're going to manipulate this a little bit, and then we're going to go ahead and take logarithms because I need to bring that power down somehow. So I'm going to go ahead and divide both sides by 4 to get e on one side, and then that's 17 over 4 on the other. And now if these two are exactly the same, if I take the natural log of each, I should still end up with the same answer. And the nice thing is, when you take natural log of e to something, it cancels out, so you just get 2x plus 1. On the right-hand side, you get natural log of 17 over 4 still. So you want to solve for x, so we subtract 1 and then divide by 2. So this is our answer exactly. You can plug it in to get a decimal approximation, but just make sure you're paying attention to what the instructions tell you on your homework and on any test. Okay? You might also do something slightly different and get a different looking answer, but it'll still be equivalent. Right? Now let's try one more. We've got e to the 2x minus 4e to the x minus 5 equals 0. So I've got a few different e to the x's going on, so I can't really solve for one specific variable at this point. I can't combine the e to the 2x and the e to the x, but one thing I want to notice is I've got an exponent here and I've got double that exponent here. So this is going to be a great time to make a substitution. So we're going to let u equal e to the x. So when I square it, I'll get u squared is e to the x squared, which really just is e to the 2x. So our equation is going to become u squared minus 4u minus 5 equals 0. And this is something I can actually solve. It factors really nicely as u minus 5 times u plus 1 equals 0. So I get two possibilities, u is 5 or u is negative 1. So be careful. I have to go back to my starting variable because I want x values. I don't want u values. But I'm going to utilize this substitution to our advantage. U is just e to the x. So instead of this u, that's the same thing as e to the x equals 5. And then you can go ahead and take a natural log of both sides to get that e to cancel out, or rewrite it in that logarithmic form. So I get one solution, x is the natural log of 5. Now if I go back to this other one, I get e to the x is negative 1. And you might notice here you have a bit of a problem because e to anything should give you a number greater than 0. So really this isn't going to work. But if you weren't 100% certain, go ahead and take natural log of both sides. And this is telling us x is equal to the natural log of negative 1. And that is a problem. Can't do that. This is undefined. So I really just get a single solution. X is the natural log of 5. Now you absolutely could check this. Gonna be a little bit difficult to actually do, but at least check to make sure something is not extraneous. So you can't just leave it in this form, okay? So now let's try another one and let's solve and ultimately round to 3 decimal places. And we've got 15 is equal to 7 to the 3 minus 2x. So again, definitely can't write 15 as base 7, but I need to get this x down. So let's go ahead and take the natural log of both sides. We get natural log of 15 and then natural log of this exponential piece. And then one of our properties tells us anything that's an exponent can just pop right out front. So I get natural log of 15. On the right hand side, I'll get the exponent times natural log of 7. And now I can go ahead and solve for x. So I'm going to divide by natural log of 7 on both sides to get natural log of 15 over natural log of 7 is 3 minus 2x. Then I want to solve this for x, so let's go ahead and rearrange it. Let's add 2x over here, add 2x over here, and then subtract this kind of grotesque number just to make our signs a little bit easier. And so by doing that, we're going to get 2x is equal to 3 minus natural log of 15 over 7. And you just want x, so you go ahead and divide by 2 or multiply it by a half. And so if you plug this into your calculator, you'll get about 0.804. Now one thing to note, you can solve this a few different ways. You might get a different form in that exact answer, but you'll get that same decimal approximation. So if you end up with something different, don't fret. It's probably the same thing. You just might have applied those properties in a different order. Okay? Now the thing we really want to be careful about, we're going to move into these logarithmic equations, and you have to be careful. You need to make sure you check your solutions because we know we can't take the logarithm of a negative number. So you might end up with something, but then it ultimately doesn't work in the domain of that function. Or it's just something that's completely extraneous. So just be very, very, very careful with these. So let's go ahead and solve each equation exactly. So I've got log base 2 of 3x minus 1 equals 3. And I don't like logarithms. I can't work with them immediately. So best thing I can do here, let's rewrite an exponential form. So this is our base, our answer, and our exponent. That gives us base, answer, exponent. Okay, so we get 2 to the third is 3x minus 1. That's just 8 is 3x minus 1. Add the 1 over and divide by 3. We get one solution, x equals 3. But now we actually want to check. So anywhere we see an x in this original equation, I'm going to replace by 3 and see if I do get a true answer. So I get log base 2 of 3 times 3 minus 1. That's really 9 minus 1, so 8 on the inside, and that indeed equals 3. So this is a good solution. You might end up with no solutions if this didn't actually work. So just always check. There might not be an actual answer. Okay. Let's go ahead and try this next one. We've got a few different logarithms, but they do all have the same base, so that's good for us. So we can't get rid of the logarithms immediately until we have a single log equals the same single log on the other side. So I don't want to just cancel out the logs right now. I've got to rewrite this and condense it as a single log as a single log. But one of our properties is when you have addition of two logarithms with the same base, those come together as multiplication. So we'll get log base 2, and we multiply those two arguments. And then I don't need to do anything with the right-hand side. But just like the exponential, now I've got e to the something and e to the something on the other side. The arguments have to be the same. Likewise here. I've got log base 2 of this thing equals log base 2 of 6x. Those things better be equal for this to be equal. So really we get x plus 1 times 4 minus x needs to equal 6x. So we need to go ahead and solve for x. So let's go ahead and expand that out, simplify and condense. So I can do a little bit. We can combine the 4x and the negative x. So that gives us negative x squared plus 3x plus 4 is 6x. Let's move everything over to the right-hand side to get a positive x squared. So we'll get 0 is x squared plus 3x minus 4. And that factors really nicely. So we end up with two x values that solve this quadratic equation. But I need to go through and check my answer. So I've got the equation rewritten right here. I want to check our two values, negative 4 and 1. And mostly I'm looking for, does it work in the domain? If it doesn't, then it's a bad answer. So let's start with x equals negative 4. We'll get log base 2 of negative 4 plus 1, log base 2 of 4 minus negative 4, and log base 2 of 6 times negative 4. Really, after this first one, you didn't need to do anything because this would be log base 2 of negative 3, but you have that problem over here. That's log base 2 of negative 24. Both of these cause log of a negative value, so this solution is no good. It solved our quadratic equation, but it does not work for the exponential, which is why you always need to check. So we still have one more value. Let's plug in 1. That's going to give us log base 2 of 1 plus 1 plus log base 2 of 4 minus 1 needs to equal log base 2 of 6. And you can go through and do it, but this is fine. This is fine, and this is fine. I'm not taking log of a negative number. So this will work. So our only solution is x equals 1. Okay. So let's try another logarithmic equation. We've got log base 3 of 10 minus x minus log base 3 of x plus 1 equals 1. I don't have logs on both sides, but that's perfectly okay. So what I want to do is still condense this as much as I possibly can. And when we have subtraction, that turns into division of those two things. So I've got 10 minus x in the numerator, x plus 2 in the denominator, and we've done nothing with the right-hand side. But now that this is written as a single logarithm equals a constant, let's rewrite it in exponential form again. This is our base, our answer, and our exponent. So we're going to get the base is 3, the exponent is 1, and our answer is 10 minus x over x plus 2. So we just need to solve this equation now. But 3 to the first is just 3, so we don't need to rewrite that. We'll go ahead and cross multiply, because really there's like a 1 under here. So you get 10 minus x is 3 times x plus 2. Distribute that out. Go ahead and add x to the other side. subtract 6 from both sides, and then divide by 4, and we get a single solution, x equals -1. But again, I need to check this works. So here's our original equation, and we want to plug in x equals 1. So that's going to give me log base 3 of 10 minus 1, or 9. Then log base 3 of 3, and that needs to equal 1. So let's full check this out. Again, we can condense this by dividing those two arguments. And so this is telling us log base 3 of 3 equals 1. So we're good. It works. Okay. So now the last thing we're going to do is another example working with those interest formulas. So now we know how to solve exponential and logarithmic equations. Let's apply that because that interest formula has exponents in it. So we're wondering if 9,000 is invested in a savings account that earns 6% interest compounded continuously, how many years will pass before there's $15,000 in the account? And we want to round to 2 decimal places. So basically, I've got this initial amount, I know how much I'm earning, but I ultimately want 15 grand. So how long do I have to wait before that's going to happen? And because it's compounded continuously, that tells us we're going to need the formula A equals PE to the RT. Our amount we want is 15,000. The principal we're investing is 9,000. Our rate is 6%, so that's 0.06. And the time is the unknown. That's what we need to solve for. So plugging those pieces in, we get 15,000 equals 9,000 e to the 0.06t. So go ahead and divide by 9,000. You get 15,000 over 9,000. It's left with our exponential. And then let's simplify this. Those zeros are just going to cancel each other out. So you get 15 over 9 equals e to the 0.06t. So you can rewrite this because it's got base e. So that's the same thing as doing, we can take natural log of both sides. To get natural log of 15 divided by 9 equals 0.06t. Dividing by 0.06 gives us our time. And if you plug that into your calculator, it's about 8.51 years. So ultimately, it'll take about 8.51 years for our amount to reach 15,000. Okay? So it'll take a lot of practice just to figure out which technique you use because there's no set standard equation you're going to be solving. But just keep in mind your properties and keep in mind that you need to check, especially with the logarithms, because it's very easy to get extraneous solutions.